Okay, thank you. I will try my best. Please let me know if you can't understand me at all, then Rachel will take over. But I'll try. So yeah, thanks for the introduction. I'm Ylva. I'm a research scientist at Ubisoft La Forge. So this research was done there. So in video games, humanoid characters are generally animated using motion capture technology, and then these animations are adapted in-game to enable interactivity and response to the environment. So one of these adaptations are so-called look-at animations, where maybe you can spot a few in these videos. And these look-at animations direct the character's torso towards a target. These lookats are generally generated procedurally with some kind of graph logic that mixes predefined animation curves. I wonder if the timing's on. So because it's just using a procedural method, it really can sometimes have a very robotic feel. So its main limitation of this approach is really its one-size-fits-all procedural approach that has a robotic feel, especially on top of usually good mocap body animation. And this can really break the illusion of having a thinking, feeling character when you then have the robotic animation on top of it. So in this work, we produced a neural network controller to generate look-at animations with greater expressivity. So what we want to enable is, for example, for this character here, to produce a shocked look at the character, whereas, for example, this one may look scared and be more like this. Then on the bottom scene here, we want, for example, this character to be perceived as a tourist. So we want them to look very curiously at all their surroundings and show interest. Whereas, for example, this person, we want them to be perceived as going to work on the same path as they go every day. So they won't be particularly interested in the landmarks around here. So they will only briefly glance at them. So to summarize, our goal is basically to automatically generate these look-at animations in different emotional styles, And we want to control the style separately for the engaging and the disengaging motion. So for example, we want the character to look at an object on the street neutrally and then see that it was maybe a dog poop and look away disgustedly. So show a different emotion on the turn away. There was very few or no previous works doing what we wanted to do. There's a couple that I want to highlight. The first is a fairly recent work, the real-time multi-map ... It is a procedural controller that uses parameters that are, such as their velocity, that are derived from mocap. And procedural parametric controllers are actually the bulk of the work in this area. However, there's another second work, which is the only neural network work I'm aware of in that field, by Klein and colleagues, the second one on the bottom. It is a neural network, but is only defined as gaze pursuit, so only gaze following. It cannot handle gaze shifts, so not looking at one target and looking away. As there was no previous work, there was also no previous data set that we could use. So we recorded our own data set to train for this purpose. First, since we wanted to model different emotional styles, we had to select different emotions that we wanted to model. And for that, we were first inspired by Plotchnik's wheel of emotion, and then in discussion with an animation expert, selected specific styles. And our goal was really to capture clear anchor emotions across an emotional spectrum to cover a variety of different reactions. It was also important to us that the styles that were perceived would be very distinct and consistent. So they should be consistent across different expressions of the same style. So for this, we developed an exact acting guide reference, again by working with an animation expert to create reference videos for each emotional styles. So reference videos how each emotional style should be portrayed. And these videos were then used to both prepare the actor before the shoot and to redirect them during the shoot to really ensure this consistent and expressive expression. So specifically, we selected the 10 styles that are listed here. The first 3 can be seen kind of as variations of neutral, and the number 4 to 10 are our more emotional styles. And for numbers 4 to 10, we captured 2 intensity levels each. So 2 intensities of the emotion. And we captured full body motion capture, and you can see recordings from the capture here. And we captured about 700 look-ats in total, so 700 look and look away. So each of these look-ats had, as I said, 2 emotions. So the actor was directed to look at a target with 1 emotion and look away from the target with a second emotion. And we captured just various combinations of these different emotional styles to capture as much variety as possible. Though, of course, it's impossible to capture all possible combinations. Okay, so now let's look a quick look at our neural network model, an overview. So the input to our model is the torso start orientation, the target look-at angle where we want the character to look, as well as 2 styles that are given as an example motion clip. So 1 style example is given, obviously, is the engaging emotion, and 1 for the disengaging emotion. The start and the target rotation are first passed to a feed-forward simple encoder that produces the motion content encoding. Then the style examples are encoded by a variational autoencoder. Sorry, my timing's on. How do you remove the timing from the slides? It keeps switching by itself. Sorry. Okay, then, as I said, the style encoding is passed to a variational autoencoder. We get the style encoding, and then those 2 encodings are concatenated and passed to a transformer decoder. And this transformer decoder then produces the final animation. And the final animation is defined for the central joints of the character, which is the rotation sequence for the head, neck, and spine. So we then conducted a user study to evaluate our results. We evaluated both the perceived appeal as well as style expressiveness of the animation. In our user study, we had 4 different motion conditions. The first that you can see highlighted here was motion capture. This is an example of motion capture take, and it just represents the ground truth with the maximal expected quality. Secondly, we have animations produced by our model, again highlighted here. Thirdly, we had a simple procedural baseline that served as a low bar for the comparison, so expected to be the lowest. And then thirdly, we had a motion matching condition that used just a custom implementation of motion matching that used some information about the style, the average velocity information for each style, which means it contained some style information, but came at a high memory cost compared to having a neural network, because it had to obviously store all the animation sequences. So the procedural condition here is the only condition that is identical across the different styles, so producing the same expression across each style. Now let's look at some results. Please note that all the face animations generated in these videos are procedural, so they're not part of the work. They're just the same across each condition. So we're looking really at the head animations. So first, here we have an example of an angry to angry, so angry engaging and angry disengaging style. And you can see in the mocap that its key characteristics are really that it's a very jerky motion. as well as a disapproving downward nod at the target. And I hope you can see that our model reproduces it quite well. Sorry, it keeps skipping. Our model produces it quite well, also producing the same jerky motion and downward nod at the target. Okay, the next example is a fearful engaging to a happy reaction. So the key characteristic of the fearful motion is really a very sudden turn, so a startled sudden turn. And the happy reaction is this sideward sideward tilt of the head, like, oh, cute. And then, how do I stop this from skipping by itself? And then, I'm sorry, I'll try to remove the timings or something. Here, sorry. Okay, so the headward side tilt, and then a kind of round backward motion. So it's like, oh, cute, and then kind of a happy, like, motion backwards. And again, you can see this hopefully reproduced quite well in our model, whereas as expected, procedural is just very robotic, and motion matching is a bit more realistic, but doesn't really have those style characteristics. Then we have neutral to disgust. So neutral is obviously just neutral, and the key characteristic of disgust is this chin downturn at the target, like ew, and then an overshoot into the opposite direction when turning away, like looking and then ew, looking away. And again, I hope you can see that in our models it's reproduced quite well. Finally, we have surprised to sad. So surprised is characterized again by a very sudden turn, a startled turn to the target, and the sad reaction is this this drop of the head, the slow sad drop, and then a slow backward motion. Looking at our results for the user study, we can see that our model was rated on par with motion capture, with both respect to appeal as well as style expressiveness. So mocap is green here, and ours is pink in the second column. And as expected, the procedural condition in blue performed worst across both measures. And motion matching was somewhere between, so it was better than procedural, but it was rated significantly worse than both ground truth, mocap, and our model. So now I want to go back a little bit to our model. So I mentioned before that our style encoder is a variational autoencoder. So variational autoencoders are known for having usually quite well-behaved latent spaces where you can do nice interpolations, etc. So what we wanted to do is explore style interpolation within that space to enable even more variety of expressiveness. So first, we can inspect our latent space to see if it actually is well-behaved, what it looks like. So this is basically just latent encodings plotted with a two-dimensional principal component analysis, so we can see it in 2D. Each dot represents one clip. So again, one lookout clip, which means it contains an engaging and the disengaging emotion, which is listed as the label. And then the bars after the labels indicate the intensity of the styles. So 2 bars is the highest intensity and 1 bar is the lower intensity. And we can see that clips of the same style are clustered quite nicely, so they neighbor each other in the latent space. We can also see that examples of the same style but different intensity neighbor each other nicely in the latent space. So here, for example, the fearful level 2 and fearful level 1 are close to each other in the space. And finally, we can also see meaningful placement of clips containing multiple styles. So first in the center, the green, we can see angry is clustered in the center there. And then the neutral reaction is here at the bottom, the light green. And then if we have a clip that contains an angry look at and a disgusted reaction, then these clips are clustered nicely kind of between the two of them. So this just validates that we have nicely behaved latent space. And now to mix styles, we can look at our architecture again. So this was our architecture. Now to mix styles, we basically just encode multiple examples. Let's say 2 examples. We encode each of these examples with our VAE. For each of these, we get a style encoding. We blend these encodings, and then this blended mixed encoding is fed, concatenated and fed to the decoder. And now we can look at some results. So all of these samples shown now are generated by our model. On the top left, we can see the neutral look at with the disgusted reaction, and we can see again the characteristic chin downturn and the head turned away towards the opposite direction when they're returning to the facing forward. And below it is, again, the angry, so the more jerky sudden turn towards the target and a bit of a jerky head nod down at the target. And in the mix now, in the second column, we can see elements of both of these styles being represented. So we can see both the chin downturn at the target from the disgust and the turn away towards the opposite direction from the disgust, as well as showing overall more jerky motion as it is in the angry style. And secondly, we can mix the happy style. So we have like the side tilt of the happy and blend it with the disgust again. And we can see in the result that we both have this sidewards tilt of the head for happy and the chin to chest more from the disgust. And then blending happy and fearful. In the bottom right corner, we can also see still the happy tilt at the target from happy, and then also the fearful backwards jerk of the fearful reaction. Okay, that's thankfully it. If you have any questions, I will do my best to horse them at you. Okay.